In this lesson, we're going to look at solving problems using obtuse triangles. At this point, we can put everything we've learned from acute triangles, obtuse triangles, and our previous knowledge about primary trig and right-angled triangles all together, and now we can use all of these tools to solve problems. If we look at this flow chart here, this will help you decide on what the appropriate strategy is. It says draw and label a diagram with all the given information. Once you've done that, you're going to make a choice. Is this a right triangle, an acute triangle, or an obtuse triangle? Once you've made that decision, then you can decide from there what the best tool is to use. Knowing that if you choose to use the sine law, you then have to decide how many triangles are appropriate. So it says when you know the lengths of two sides and the measure of an angle that is not contained by the two sides, the case may be ambiguous, and this is that side-side angle case. And then you're deciding, is it one triangle, two triangles, or are there no triangles that exist? Let's take a look at two different examples where we're going to use these tools. Example 1, visualizing a triangle to solve a problem. The children's slide at the park is 30 feet long and inclines at 36 degrees from the horizontal. The ladder to the top is 18 feet long. How steep is the ladder? That is, what angle does it make with the horizontal? Assume the slide is straight and that the bottom end of the slide is at the same level as the bottom end of the ladder. Alright, so we can start by drawing this diagram. If I start here, I'm going to put my 36 degrees here, which means this would be 30 feet. That's the length of the slide. And then I've got an 18 feet long ladder, so I'll make this 18 feet. Now obviously I haven't drawn this to scale. It looks like the slide and the ladder are the same length. If you want to change that, we can do that. Make the ladder shorter. That would make a little bit more sense for our diagram. Alright, we don't really know anything else for this diagram, so I'm going to label this A, B, C. And now I have to decide how many triangles there are. I can see that side A is smaller than side B, so I'm going to figure out what the height is here to see how many triangles I have. To solve for the height, I'm going to use sine. Sine of 36 degrees is opposite, which is my height, over hypotenuse, which is the length of the slide. Solving for h, we have 30 sine of 36 degrees. Punching that into my calculator here. Get 17.6. So that means that this is the two triangle case, because my h, my height, is smaller than side A, and the length of the slide is bigger than side A. So A is between those two values. This is the notation to tell us that A is between the values of h and b. And this is the two possible triangle case. One thing you want to note though is just because the situation says that there's two triangles, what would that actually look like in terms of a slide? So if everything else stays the same, this is still 30 feet, we would have an obtuse angle here. This would be 36 degrees, this would be 18 feet, and this would be side B, side A, and side C. Well, if this is the slide and this is the ladder, you can see that that makes sense for the situation. I forgot a T here. But if this is the slide and this is the ladder, Structurally, that doesn't make any sense. You're going to be climbing the ladder at an angle under your slide. So just because mathematically there are two possible triangles doesn't mean that there are two possible triangles for the situation that you're trying to solve. And that's something that you're going to have to be aware of when you're solving for these questions and doing these problems. So let's solve the first triangle, and then we'll write an explanation as to why the second triangle doesn't make sense. So solving for the first triangle, I'm going to label this B1, C1, B2, C2, just so that we don't get these mixed up. If I solve for the first triangle here, I'm using the sine law with side A over sine of A. Actually, I should do it the other way if I'm solving for my angle, save me some mathematical steps. So sine A over side A, and then sine of B1 over side B1. Substituting in, I'd have sine of 36 degrees over 18, and I'm solving for sine of B1 over side B1, which is 30. Cross multiply and divide, and you're left with sine of B1 is equal to 30 sine of 36 degrees all over 18. But I want to solve for angle B1, so I'm going to inverse sine all of that stuff. Alright, so let's punch all of this in. So inverse sine, our numerator is 30 sine of 36, denominator is 18. We get an angle of 78.4 degrees. Now, had you not recognized that that situation didn't make sense right at the beginning, you would go ahead and solve for angle B2. You would take 180 degrees minus 78.4 degrees, because this is the supplement, and you would get that angle B2 is 101.6 degrees. And hopefully at that point you would see that this angle is impossible for this situation. The ladder would not support the slide. So in the end, we can conclude that the angle the ladder makes with the horizontal is 78.4 degrees. So again, just because you can figure out that there are two possible triangles doesn't mean that the second triangle actually makes sense for the situation. So make sure you're reading carefully, drawing proper diagrams, and then analyzing the situation for what we need in the problem. Example 2. Visualizing a triangle to solve a problem. A surveyor in a helicopter would like to know the width of Garibaldi Lake in British Columbia. When the helicopter is hovering at 1,610 meters above the forest, the surveyor observes that the angles of depression to 2 points on opposite shores of the lake measure 45 degrees and 82 degrees. The helicopter and the 2 points are in the same vertical plane. Determine the width of the lake to the nearest meter. So I see the biggest challenge in this problem is actually drawing the problem. It's hard to understand exactly how we're supposed to draw this till we start doing that. So what I'm going to do is I'm actually going to draw the lake to start with. And we'll label it the lake so I know that that's what it is. Now it says the surveyor observes that the angles of depression to 2 points on opposite shores of the lake measure 45 degrees and 82 degrees. So if the surveyor is here, the surveyor is measuring further away and closer, right? So those are our two angles. let's label these points A and B. So those are the 2 points that the surveyor is looking at. Now, in terms of the angles of depression, if we use that as our horizon, we have one angle, which is the 82 degrees, right? And then we've got the other angle, which is the 45 degrees, and this is from the horizontal. So let's just make this bigger so it's easier to label. So this is our 45 degrees in here. And this is our 82 degrees. This whole angle is 82 degrees. Alright, what else do we know? It says when the helicopter is hovering at 1,610 meters above the forest. So that would be this vertical height. We could actually put that in as a 90 degree, because when we're talking about any sort of height, that has to be a perpendicular height. So that height is 1,610 meters. Alright, and we want to know the width of the lake. So from the information given to us, we can figure out some of our other angles. If we know this angle in here is 45 degrees, then we know that the angle in here is also 45 degrees. So that's helpful. And same goes for our 82 degrees. Now, the 82 degrees is a little bit different because it's on the outside here. That 82 degrees would actually match the 82 degrees in here using our angle properties. And if we do that, then we can figure out the corresponding angle out here. So if I make this smaller, we can go 180 minus 82 to figure out this other angle in here. So if I do that, 180 degrees minus 82 degrees, we get 98 degrees. And that would be the angle in here. Now we could go 180 minus 45 minus 98 to get this angle in here, or we can just go 90 minus 45. Either way, because that would be complementary, we can get that little angle inside there to be 37 degrees. Now I haven't started looking at my tools yet for what I'm going to use in order to solve for the distance of the lake. I'm just starting to set some stuff up here, right? Figuring out what I can solve for in order to figure out that distance of that lake. Now at this point, I would like to use the sine law, but all I have for solving the lake is the 37 degrees, and then the lake is unknown. But I don't know what this distance is, and I don't know what this distance is. There's no other information for this big triangle in order to solve. I can, however, use the 1,610 somehow, and maybe the 82 degrees to figure out what this is. So let's call that A, since it's opposite angle A. And if I label that according to the 82 degrees, the height, that would be my opposite, and side A would be my hypotenuse. Opposite and hypotenuse is sine theta in our primary trig ratios. So in that case, it would be sine of 82 degrees. Opposite is that 1,610. Hypotenuse is what I'm solving for, which is A. Cross multiply and divide, and I get that A is equal to 1,610 divided by sine of 82 degrees. Punch that into my calculator. I get a distance of 1,625.8 meters. Alright, so I'm going to use another color here and erase some of this extra information. So let's use green just so that we can see that that's something we solved for. So now that I have that distance, I have that pairing up with angle 45, Then I have the 37 degrees pairing up with the distance that I'm looking for, which is the lake. I'm going to use S, I guess, lowercase s, for solving for the lake. So let's set up sine law. So that would be, if I'm solving for s over sine of s, and then a over sine a. In our case, s is what I'm solving for, sine of 37 degrees, and then I've got a, which we just solved for, over sine of 45 degrees. Get s isolated, and we would have s is equal to 1625.8 times sine of 37 degrees all over sine of 45 degrees. Let's go ahead and put that in our calculators. 1625.8 times sine of 37 all divided by 1000, sorry, not 1000, sine of 45. And we get 1,383.7 meters. And that's the distance of the lake. So we can write, therefore, the width of the lake is 1,383.7 meters. That's it for today's lesson, and that's the last lesson of the unit. Thanks for joining me.